Okay, hi everybody. I am Tyler Morgan. I'm a scientist in the functional MRI core facility here at NIH or NIMH. And today we're going to be talking about functional MRI at 7 Tesla. This is kind of in some ways, a two-part lecture. So next Thursday, I'll be talking about Lara fMRI, and I think that those two are pretty well entwined. But today we're going to be talking about the generalized form of 7T and what it can be used for. And then next week, we will talk specifically about going to high resolution in order to look at layers. Okay, and in that kind of space, I am going to figure out how to use PowerPoint. Okay, so just from the general point of view, functional MRI at 7T or even higher fields, we'll be very general about it, is basically most of the time, I would say, used in order to try to gain more signal that can give us, which kind of translates into higher resolutions, etc. There are other applications of it, particularly in things like spectroscopy, etc. But today we're mostly going to be talking about signal and resolution. So obviously, if you want to scan at ultra high field, you need an ultra high field MRI machine. And this can come in the form of things like what we have at NIH, like our 7T-A, 7T-B. We also have an MRF 7T, but it can also include higher fields. So these can include 7 Tesla, 9.4 Tesla, 10.5, 11.7, or there's even a project coming up at 14T, hopefully. But these magnets grow pretty exponentially. So you'll see a little bit in this conversation that the engineering challenges that happen at 7T and higher increase as you go. Okay, so how many 7 Teslas are there in the world, or how many ultra high field systems are there in the world? There's a really convenient map that's maintained by a previous colleague of ours, Renzo Huber. That's just a Google map. It's really nice because you can basically pinpoint every center that has one. It's kind of ages me, but when I started doing 7T MRI in 2015, there were about 40 machines in the world at the time. It was a really rare technology. Today there are about 140, which is awesome. It's growing. It's an increasing field. We're nowhere near what we would see in the world of 3T, where you have about 20,000 scanners worldwide. But still, we're getting there. In addition, I'll just point out that about 45 of those machines are in North America, in both the United States and in Canada. And I think it's always impressive to point out that 3 of those machines, 3 of the 45 in North America, are in this building. They're just right over there. But I want to ask a quick quiz question. Some people have heard me ask this before, so you'll refrain from answering. But does anyone know why we call it ultra high field fMRI, MRI? Any guesses? No? Okay. Well, ultra high field MRI, you might think, is just because the magnetic field is really strong. In some ways, that is correct. But it specifically refers to the different wavelengths that are used for everything in the world. There are standard bands of frequencies that we refer to. And one of those actually is ultra high field. So ultra high field refers to any kind of wavelengths that we look at in signal processing that are in between 300 megahertz and 3 gigahertz. And then if we look at the frequency of rotation of water protons when they are in a 7 Tesla MRI system, it comes out to 297.99 megahertz, which is just close enough that we can call it 300, and then we can be in the ultra high field segment of frequencies. So hopefully this comes up on a pub quiz someday and you can answer this, but it might not. Okay, so why do people actually use 7T? Well, the simplest way that we can actually think about this is just that you get increased signal as the strength of an MRI system gets stronger. And that's really important. There is some debate on how much stronger it actually gets. You have a screen on that side as well? Yeah. Oh, great. And I'll kind of walk through a little bit what this means. So basically, if we account for the signal strength just on its own, so in other words, the rotational frequency of protons as well as the magnetization, we would expect that with every increase in Tesla of magnetic field, what's called B0, so our static magnetic field, you would go up in a squared fashion or a squared function with your signal. So if you went from 1 to 2, you would have a 4 times increase in the amount of signal that you would get. Turns out that this is not completely the whole story. And people have gone through the different aspects of how the signal actually behaves by accounting for things like thermal noise. Thermal noise is the noise that is associated with the fact that we are building things out of electronics in a non-perfect world. So basically wires are not perfect, or your receivers are not perfect, etc. But basically there is always noise that is inherent to systems. This is called thermal noise. Alternatively, we lose a little bit more signal if we also include the coil quality. So in other words, like how well are you actually building your coils and how sensitive are they to whatever it is that you're trying to pick up? And then it gets even worse. It actually goes down from a squared relationship down to just a linear relationship if you include information about the thermal noise, the coil quality, as well as the fact that whatever you're putting in that MRI machine actually has its own conductivity. So in other words, when we take a person, which is a relatively large sample of protons, and you put them inside a magnet, you are actually disturbing the magnetic field and the electrical system in a way that you lose signal just by having that thing that you want to measure in there. But it's not all so bad, because it seems that the empirical data that we've recorded in the field is relatively in the middle of that. We're better than we could be if we accounted for every type of noise that we have. But at the same time, we're not so good that we're only seeing signal. We still have some noise in our systems. And it turns out that the relationship is around, or this is a little bit theoretical, but it's around B0 to the power of 1.65. So this is a little bit lower than if we only accounted for thermal noise itself, but it's higher than the rest of them that we saw. And I just want to point out that this actually makes 7T a pretty good deal when it comes to what types of systems do you want to scan on. It means that you have a pretty good increase in your SNR in comparison to 3T systems, which we saw are incredibly common in the world. Well, very common in the world. But we also avoid some of the intense engineering challenges that happen at really, really high fields. And just to drive this point home a little bit, I guess, if we look at very similar resolutions, we will notice that when we go from something like a 3T system, where you can get some of these high resolution signals, up to 7T, you'll see more details come out because the signal is getting stronger, your statistics get better, your noise sources are different, etc. As you go to 9.4, we can do the exact same thing, and you'll notice that the detail is largely the same, I would say. You do get an increase in the amount of signal, but you also, that comes with a lot of problems. Even just looking at the anatomical images in the background of these two examples, you can already kind of see that there's other stuff going on. There are inhomogeneities, there are different things that are happening that are probably hard to deal with. So we're just gonna, for right now, focus on 7T and go from there. And I think it's a nice way to think about this is in the context of trains. So like your 3T is your common train, your Amtrak that you can get on. I was about to say it's really reliable. Hopefully it's reliable. But then you can go to something like 7T, which is much more, let's say, specialized and works really, really well. We can think of it as kind of like the bullet train of MRIs. But it's not so crazy that it's like an experimental maglev system. It's like still usable. People can do stuff on it without having a huge engineering team there every single time. I'm sure this will come to a surprise or come as a surprise to everybody, but it actually isn't magic, and it does kind of come at a cost though. There are bad things about it as well. One of those things is, I mean, I can say that it's bad. It has good and bad aspects, but it is a feature of when you go to higher fields that even though your signal is higher, you lose it faster. So in other words, everybody's seen the MR lectures so far, and has probably also seen an MR physics textbook at some point where they basically talk about hitting a sample with an RF pulse. This causes an amount of energy to be flipped into the longitudinal plane. And then as that comes back, we're basically decaying in the amount of signal that we are trying to record. That process is called T2 star decay. And it essentially is the parameter that tells you how fast is it going to come back out of that longitudinal plane, and how fast do we need to read out in order to really see that signal. The thing that happens when you go to higher fields is that that T2 star gets shorter. And so that means even though you have a lot more signal, this is the actual model of the amount of difference in signals that you would see between a 3 Tesla system and a 7 Tesla system. So you start much, much higher, and you basically stay higher the entire time. But that difference gets less and less and less the longer you wait to read out. And that's a really important factor in MRI. In addition, I just want to point out that when you have imperfections in the system, you also have those affect your images more. So basically what I'm showing here is if you apply a gradient, which is what is required in order to create voxels and images in our system, if there are any imperfections, so here I'm just making a model where it's 1 ppm off resonance, which basically means that your shim is not perfect on your sample. The effect of that will be greater at 7T than it will be at 3T. And that gets worse and worse and worse the longer you wait to read out. And this is really important because oftentimes we really want to go to high resolution as well. And the effect of seeing these phase offsets as well as the decay that you're seeing in your signal is that you end up having some cases of distortion, and you also have some cases of dropout. And those don't happen the same places in the brain all the time. And this is because the shim is different at different positions in the brain. So areas that are really close to air, such as near the sinuses, if you care about, let's say, DLPFC or something like that, it's a hard area to image as you go to high field, specifically because the shims are more difficult to get really good there. And so that's something that you have to keep in mind when you go to higher fields. And again, just to drive this home, if we care about really small structures, distortions can be pretty dramatically problematic, let's say. Because if, let's say, we have a model from our anatomicals and we want to look at fMRI activity, we can see that the differences in distortion, whether you're pushing them in one direction or the other direction, can mean you either correctly localize or don't correctly localize those things. So I'm just flipping back and forth between running the phase encoding in this direction or in this direction. And you can see that you basically have gray matter entirely jump out of your anatomical model in one of the directions. That makes sense to everybody? Cool. Okay, so why can't we just scan faster then? Why can't we do everything in a shorter amount of time? And then we'll basically just be able to avoid all of those problems, because at the beginning of those, at close to 0 TE, we were still pretty good. Excuse me. Well, if you came to the deep sampling, sorry, if you came to the deep sampling lecture a few weeks ago, we learned that one of the ways that you can get more signal is always just to scan for longer. That's pretty simple, and it gives us really good data. In the case of actually like reading out a lot of information, particularly in resolution, this can result in things like these images, which hopefully you can appreciate from where you're sitting, but like these are 250 microns, so 1/4 of a millimeter resolution, but it takes 3.5 hours. But it's very, very detailed. So what they are basically doing is using really long scan times in order to accumulate more and more information about the person's brain, and then they can get really good images. Alternatively, like we just learned, we can also increase our field strength, which gets the same amount of signal, but in shorter times, etc. But there's something that's kind of in between these two. And it's a little bit of a tangent, but I want to talk a little bit about how do we actually accelerate our scans in order to make sure that we're not scanning 3.5 hours every time we want to get a picture of someone's brain, etc. So we're going to talk about how do we image faster while also increasing resolution. Okay, so our goal in MRI is basically to record from what's called K-space, which is basically the frequencies of the images that you want to record from as quickly as possible, because we want to cover as much of that K-space as possible in the shortest amount of time to avoid distortion. So this would be the case that we could just see the entire K-space. It's kind of pretty. And then if you perform a Fourier transform, which is basically just converting all of these frequencies into their corresponding pixels, you can create a picture of a brain. And this was covered a little bit by fMRI in lecture 3. So if you want to review that, you are welcome to. But that doesn't tell us anything about how we can actually go faster. Well, the best way that we have found to go faster in MRI is to actually just don't record that entire space. Assume that you don't need the entire thing. So in other words, here we're showing an example where we have this full K-space that we saw here, but we're just recording half of it. So it takes half the amount of time to get through it. We're basically just skipping every other line. The problem with this is that when you perform a Fourier transform again, you can see that we didn't just get the middle of the image. That would be really convenient. It's more like how optical cameras work. But when you're recording from frequency space, you always have the entire object recorded. You can't avoid that. It's also why sometimes if anyone's been at the MRI center and you've had a field of view that's shorter than the object that you're actually looking at, you tend to get like the nose coming in through the back of the head, etc. It's the same principle, but here it's because we're skipping lines, which makes it so that the resolution in that direction is half as large, or half as small, I guess. Okay, so one way that we can try to deal with this is to take advantage of something that is kind of a separate technology in MRI, but is just as important for understanding how we can get more signal from the system. And that's called parallel imaging. Parallel imaging is essentially the idea that you can get better and a little bit more signal if you take more than one receiver in the MRI system and kind of localize them so that they are better in one part of the brain than in another part of the brain, or different body parts, etc. And what this ends up looking like is essentially that multiple coils are going to have different spatial distributions on what it is that they can see well and what they cannot see well in your MRI system. So here I have just an example of a full brain. This is a real person that we've put in. And we have two theoretical coils on either side. And basically, these coils have different views of the same object. So in other words, if we were to reconstruct only from this coil, we would get something that looks like this. And if we were to reconstruct only from this coil, we would get something that looks like this. And this is because the information that is closer to that coil is going to be better read out, and the information that is far away from it is going to struggle. So it'll fade kind of to black in the perfect case, or probably more realistically, it'll fade to noise. And then what we can do is we can actually take these two images and put them together, either by averaging or by some squares or some kind of clever way of doing it. And we can get the whole image at higher quality than if we had only one coil that was covering the entire brain. And what this actually looks like in practice is essentially so when you look at a piece of hardware, which these are the receiver coils that we often use in MRI, on the inside of that, you actually have a whole bunch of little coils that are specialized in different parts of the brain to pick things up, if that makes sense. Now, the cool thing about this is that you can use this information in order to gain acceleration when you're scanning. And I've laid out what different images are going to look like if we were to combine the last two slides that we just saw. So we have multiple coils that we're reading out from, and then simultaneously we can also skip part of K-space. So in other words, let's say we have two coils, and we have now skipped half of our K-space lines so that each of our images that we're reading out, they look like those ones where everything was folded over, but this time they're actually different images. So in other words, this one is more weighted towards the left-hand side. And this one is weighted more towards the right-hand side. So it's coil 1 and coil 2. And for convenience, what I'm doing here is I'm basically labeling them as the order that they should be laid out in order to get the best image that you can. So in other words, if they are here as B, A, D, C, and we just cut them in half and we rearrange them so that you have A, B, C, D, you can see that now we have the full image that we wanted to get, but it has these repetitions on them. And we want to know, how do we actually get from this to a full image? And there are multiple algorithms that you can use for this. One of the really common ones, or one of the ones that has been used for a long time, I guess, is called sense or asset, depending on which vendor you're with. And the idea behind sense is that you want to actually map out that brightness that we saw on those previous images. So in other words, if we looked at our coil 1 or our coil 2, and we just said, okay, on the full map, we're really weighted towards this side of the image, but we have very little information from this side of the image. And then the same for the next one. So in S2, in coil 2, we also have black on this side and white on this side. Then basically we can take that corresponding, we know from how we sampled through K-space, which voxels are going to be overlaid on top of one another, because we're basically just folding the whole thing in on itself. So we can take this green voxel in this image and the green voxel that came from coil 2, and we can actually make them into a linear model that makes it so that we can actually solve for which parts came from which side, because we know which coil was closest to them. So in other words, in S1, the green is equal to blue times yellow plus red times purple. So in other words, it's a product of the sensitivity maps multiplied by the information that you're actually recording from in these measured information. And then that way you can kind of pull everything apart and you can get great images based on half of the amount of k-space. So in other words, what we needed in order to solve this was we got to cut our k-space in half as long as we had 2 coils to work with. So you can imagine that if you have 32 or 64 or 128 coils, you can get huge improvements. I'm quickly going to go over another really common way that people do this problem, but the visualization is maybe a little bit harder to picture because this one is not in image space, it's in k-space. So in other words, we're working entirely within the framework of the frequencies that we're recording from. And basically how we do this is called grappa or arc, depending on which you're using or which vendor you're at. But basically what they do in grappa is that they skip half of the lines. Here, the red is the lines that we actually recorded. So you can see all the data points that we have here from coil 1. We don't have anything from line 2, but we do have stuff from line 3, etc. But importantly, we actually increase the amount of information that we record from the area of the highest signal. So the middle of k-space has the most signal. So we're going to record every line for a little while there. And basically what we're going to do is, because frequencies don't change, well, how frequencies contribute to the image does not change that much if you go one line to the next line, because you're basically just having very tiny changes in the orientations that you're representing and very tiny changes in the spatial frequencies that you're representing. So we know that there's a lot of overlapping information there. And so basically what we're going to do is we're going to build a linear model from the information in the middle of the image that will tell us how we can actually fill in those data. Hopefully people on the OWL can still hear me from here. But basically, once we have built this model, we can then go to missing data and we can say, if we take all of the coils and all of the locations that are near a point that we want to fill in, we can just build a linear model that is most of the time pretty accurate. And then you can just fill in all of that information and reconstruct it as per normal, which is very clever. I'm not going to go too much into the math of what this actually is doing, but grappa is kind of proven to show that like you have all the information always. So it's just a matter of like, how much noise are you competing against? Okay, as is the case with everything, there are always limitations to acceleration, but you're basically limited by the number of receiver coils that you have, as well as their arrangement. If you put all the receiver coils on the back of the head, you'll do really well in visual cortex, but you'll never see anything in the front of the brain. This is pretty common in visual studies. If anyone's ever had any interactions with those, the images always look weird. The other really important thing to keep in mind is that noise contributes to these systems. I alluded to that a little bit with the grappa example, but it's important to realize that that noise is actually distributed in kind of interesting, weird ways. And that's based on how you actually sampled from your data. So if you skip every other line, oftentimes what we have is our repetitions will all go in the same direction, because the Fourier transform is actually unwrapping only in a specific direction. So that's why we get images that have wrapping only in this direction rather than in the other direction. If we had skipped lines going this way, we would have the opposite. And what that basically means is that the missing information that you're actually trying to fill in, whether that's in image space or in k-space, those will actually be sensitive to whether you were picking up on small amounts of noise that would have been associated with those, so that you can have tiny fluctuations that you're just not picking up on. And this is what's called a G-factor map. This basically is a very predictable map that you can actually get for a lot of the things that you're doing in MRI. And what you can see is as you accelerate more and more, so here we have half as much, well, we have a quarter of as much data because we're going half as much in one direction, half as much in the other direction. So we would have repeats in both direction, sorry, this direction and this direction at the same time. But you can keep going. You can have a third in each direction or a quarter or a fifth. And you can see that the amount of noise that is being contributed to your signal is getting worse and worse and worse. So here we can start to see that it's up to like 1.25. So you have like 25% more noise. By the time you're at 5 by 5, you're at double the amount of noise. So unless you were in a really strong regime of your SNR, you're probably going to be hurting a lot there. So there are limits. Also, algorithms are never perfect. This is kind of what I was alluding to. But if you have a really bad reconstruction, so in other words, grappa or sense is really messing up a lot, you're still going to have these bands that come across. And most of the time it's in the strongest signal, which is the fat at the outside. So a mathematically minded person might think to themselves, well, what if we just didn't care about the fact that algorithms are going to be really bad or potentially bad? And we just decided to make it so that we left those things to kind of be contributing to the image. So in other words, we kind of have repeats, but we just make those repeats not make any sense anymore. Because like I said, if you skip, so the example here is that we skipped every other line, and we get perfect repeats over and over again of the same image. So basically, it's just an offset version of that. If you used an algorithm that was like, oh, rather than doing that, we just randomly sampled from the image, you still have all of those same repeats, but they are no longer an image because they don't coherently come together. They're not just the other half of the missing K-space data. They are just going every direction. And this is a concept called compressed sensing, or the sampling that's associated with compressed sensing. And compressed sensing is really clever because basically what you can do is you can undersample more severely than what you would do in other algorithms, but because that information is basically just randomly projected into your reconstruction, you can actually use regularization techniques in order to get rid of it. And this is an example that we've collected downstairs. Basically what we have here is a version of an anatomical that we recorded with grappa 3, so we're only recording every third line. And here we're using the exact same thing, but we're doing it with compressed sensing. And you can see that rather than a factor of 3, we're at a factor of 5.1. So this is 35% of K-space or 18% of K-space. And this one's also much faster. But I would venture to say that the quality of these two images is pretty similar. So you basically just used a really clever algorithm in order to increase your data quality, at least to a certain extent. You could dive into this and make declarations about which one is better, but I'll leave that for you to do. That was a very long tangent of how recon works, but I think it's really important for everyone who's thinking about doing 7T to kind of understand some of the algorithms that enable us to actually get data out of the machine. And I would say that acceleration is a pretty important factor in us being able to get good quality data from 7T. Okay, but I'm going to ask the question, is 7T actually better for fMRI then? Like all of the stuff that I've talked about so far has been like, yeah, it's good, but it's also bad, blah, blah, blah. So the physics show that 7T should be better, but is it actually? Generally, yes. I would say that under a lot of circumstances, 7T provides increased SNR, and it can also give you better resolution for your fMRI. And this translates to better functional contrast. And it also, importantly, isn't just about the signal itself. We're not just seeing the exact same thing, but a little bit stronger. We actually see more details from the brain. And you can see this in this example from the Human Connectome project, where basically they're looking at components from resting state, and they're finding that in the 3T, they did just fine if they took a seed voxel and said, in visual cortex, can we see the rest of visual cortex? Yeah, we can. But what they were missing is that there was a lot of other brain areas that are also correlated with that visual cortex. So if we want to make really good, important neuroscientific decisions about like what are different brain areas actually doing and how are they working together, even if they are not in the same modality, 17 may be an important factor in that. And this was backed up a little bit by other analysis. Oh, it's just hard for me to see from right here, but you guys can see it. So basically what they did was when they were looking at these components, they looked at if we do the exact same analysis on the exact same subjects in 3T and in 7T, is resting state different? And it turns out that the total number of components that they get from resting state analyses goes up in 7T. Also, the number of noise components goes up, so you can kind of separate those even better, because basically you can see which ones are actually neurological and which ones are not. And importantly, also, if you do an analysis of which ones are related most to bold, you get more as well. And that is pretty much related to the things that you would expect it to be related to. The unstructured compared to original, unstructured noise compared to original variance is lower in 7T, and the bold variance compared to the original variance is higher in 7T. So in other words, you are picking up more of the signals that you care about if you care about bold. But I will say, this is the theme of my talk, is it's good and also it's complicated. Is basically that you have to think a little bit more when you go to 7T about what the actual sequences that you're using are and what they are doing for you. So as an example, I'm showing two really common ways of recording fMRI data. The first, I'll point to this side first, is 2D multiband or simultaneous multi-slice imaging. And basically what this is doing is it's 2D. So you basically excite slices that you want to image, and then you just sequentially go through them. So in other words, what you're seeing here is we recorded the first images, and then we're just recording over and over and over again until we fill in the entire thing. So we took one slice, we recorded the next slice, we recorded the next slice, etc. And I'm pointing to two because it's using clever techniques of multiband, which means that you can record more than one at a time. That's one of the acceleration techniques that is available. Alternatively, in the 3D case, you're actually exciting the entire brain all at once, or whatever slab it is that you want to look at. And then you're filling in the K-space information one by one. So in other words, you're always recording from the entire brain, but the information that you read out from it is different every time. And that's the slices that you're filling in. So in other words, basically, these are already complete images as they come in. So you can see it's just filling in that image. Here, you start with very little frequency information, and then the more you get, the more detailed and sharper your images get. But it turns out that these two types of sequences are really good at different things. So if we were to plot the relationship between voxel volume, so in other words, what's your spatial resolution, and the temporal signal to noise of each of these, 3D EPI is really, really good at small voxels, so high resolution, but it's not as great as 2D when it comes to lower resolutions. So depending on what questions you're asking in neuroscience, you want to be able to choose the type of sequence that is best for the question that you're looking at. In the deep scanning or deep sampling lecture, we talked a little bit about this, that people actually tune the types of studies that they're looking at to these resolution problems. And so for anyone that's acquainted, the Natural Scenes database explicitly avoided 3D EPI because they were about right here. Actually, maybe more like right here. So 2D was just better for the question that they were asking. But oftentimes, if we're going to layer MRI, we would want to go to 3D because it is a better choice in that case. And you can kind of see this in the images that we actually record using these. So you can see that there's more specificity and a little bit higher statistics in the 2D for the slower resolution, as opposed to if you look at these layer profiles, you can see that pretty much this whole section is filled in on the 3D, and it's pretty messy on the 2D version. I'll also just really quickly point out that there are other things that don't quite match between these two things. 3D almost always has higher signal in general, but it has a lot of other things that come with it. Motion artifacts get pretty bad in 3D because you're filling in that whole space the whole time. And there's no slice timing, so you don't get really precise timing. Whatever your TR is, if it's 5 seconds, you're just averaging over a 5-second window of whatever the brain was doing during that time. And lastly, there's also a little bit of confusion between the TR, which is every time you fill in a little bit more of this K space, versus that 5 seconds that is the entire time it takes you to get a brain. In the 2D, you get a little bit lower signal, but you have very few motion artifacts. Actually, it's like one of the best. 2D EPI, especially single shot, is like one of the best ways we have to avoid motion in fMRI. And also, and maybe this is just a side point, pretty much everything that we have in terms of analysis and processing methods was originally created for 2D MRI, fMRI. So you have access to pretty standard processing, and you might have to do more specialization if you're using 3D. Just something to keep in mind. Okay, so we've talked a lot about like the good and the bad things that happen in 7T MRI, but I want to go a little bit into the details of what are the things that it can actually do? What results have we seen from 7T that are cool? Now, the specificity of 7T enables us to actually look at individual finger responses from tapping or from getting tapped, basically, in single subjects better than what we have seen in 3T in the past. And so what I'm showing here are actually flat maps of the portions of the brain that represent those fingers. And you can actually see that the activity patterns move as we look at different fingers. So the little finger, ring finger, middle index, thumb, and then all of them together here kind of form this cool rainbow map. That was really difficult to do previously, and it was really the advent of common processing theme or processing streams on 7T that enables us to look at this in more detail. And this is kind of an important thing because this just in itself might not seem super important, but it's provided really cool subsequent experiments that have provided valuable information for understanding conditions like hand dystonia. So these are basic science movements in the field, but they actually do make a big difference when we start thinking about how we understand different conditions. As another example of cortical column analysis or acquisition, Issa Yaqub from Minnesota showed that it was possible to actually see cortical columns using fMRI in general. This was in 2008, so it's quite a while ago at this point. But basically what they did was they took a flat, they basically analyzed a whole bunch of people's brains, and they found people that had V1 cortical sheets that were quite flat, so that they could put like one slice in there and measure it really, really well. And they were able to map both ocular dominance and orientation selectivity in V1. And you can see here. So on the left-hand side, you have ocular dominance. So basically, one of the colors refers to information coming from the right eye or from the left eye correspondingly. And then also which orientations or like lines in the world that portion of brain actually cared about. And this was a really cool landmark for human fMRI because basically this had never been seen in humans yet. So it's a type of response that we knew existed from non-human primate imaging. And particularly this is calcium imaging where you can see really awesome details, but we can see that the patterns that we record in fMRI are actually pretty similar in how they're structured, which is important. We can also look at really small brain structures in general, which is kind of exciting. So 7T can be used to create subcortical structure maps. And I should point out, so these are trying to understand different portions of subcortex in vivo. So these are in living humans. But 7T is also really good at looking at ex vivo studies. So in other words, we have some people doing this type of work here, but this is a work from Boston at MGH. And what they did was they scanned really, really, really high resolution, because you can scan a not alive brain for a very long time. And they were actually able to get down to 100 microns. So that's a 1/10 of a millimeter resolution. And I had to check like 3 times when I first read this paper that this was an MRI image, because it looks like a histology image to me. And that's like some of the power that you have in looking at these high resolution, these ultra high field studies, is that we have the power to go to resolutions that we never really thought we could before. And this actually gets translated into the clinic in pretty interesting ways. So 7T is also used in order to take advantage of its high resolution to improve diagnosis and treatment. One example here is mapping out subcortical structures like we just saw in those previous images. But here what they're doing is they're actually trying to understand what is the best route in order to place deep brain stimulation electrodes in order to make sure that it's both effective and also it's not hurting the patients in unwanted ways. And so basically we're taking really small locations in the brain. Here we care really a lot about the subthalamic nuclei and the differentiating it from the substantia nigra and making sure that we're placing things in the right place. Also in the clinical realm, anytime you have a disease that really depends on something that is really small, that's someplace that 7T is most likely going to shine. The example here is on small vessel disease as well as stroke. So here's a paper that's just comparing the differences between clinical images that are recorded at 3T and 7T in the same participants. I don't know why they didn't use the same slice here, but it doesn't really matter. But yeah, so you basically have, like, if you map out the arteries on 3T and then you go to 7T, you can just see that there's a lot more detail. Hopefully that's visible to all of you guys. But like in the places that they're pointing out, they really can't see much detail at all in the 3T system. But here they can actually locate better. And the same for the SWI below. And this can also be used pretty effectively to look at neuroscientific questions. So we're shifting back into the more basic sciences. So these are called mesovein protocols. This is something that's developed by a group in Maastricht, specifically Farouk Gulban. But basically these vascular protocols can be used to look at really, really high detail of where the arteries and the veins are in cortex. And this is quite interesting to us because arteries and veins are the basis for a lot of the signals that we care about in fMRI. So we can use more detailed anatomical information in order to interpret our data better when we're doing tasks, etc. And this becomes really, really relevant when we start talking about LAIR fMRI. So here we're looking at examples of those really high resolution arteries and veins. And we're basically looking at different vein types here. And we can actually locate when veins go through all of the cortical layers or when they only go through a few. And he's pointing out in this example that you can actually look at different layers of the surface rendering and see that you have a type V4 or V5, which is these ones that go all the way through, because you can actually see it in all the different layers. But then you can also look at other veins like this one, which is V3. It only goes partway through. And so that is useful information if you care really deeply about the cortical responses in that area. Okay. I'm also going to talk really, really briefly about the promise of LAIR fMRI. So this lecture is not about LAIR fMRI. But I just wanted to mention in the realm of 7T that there's a lot of excitement that surrounds this field. And importantly, this is related to the fact that, or one of the reasons that we're really interested in it, is that it kind of gives this promise that we can start not only looking at different areas and how they're activated during tasks or during conditions, etc., but we can also look at how those areas are connected to one another, because the cortical layers may give us clues about which information is flowing and which direction it's flowing. So that's important. But that's your one little piece of layer information that you get this week. And lastly, I'm just going to talk really briefly about kind of some of the new developments that we've seen in 7T over the last few years. I would say one of the biggest ones is the development of head gradient systems. This is actually a very old idea that has been redone recently, which is kind of a history of MRI. It's like we take old ideas and we recalibrate them to make them better. But this is what's called the next gen 7T. It's at UC Berkeley, but it's being installed in other centers around. And basically what it is doing is it's creating not the static magnet changing, so we're still at 7T, but the interior magnets that you may have seen in your MR physics books that make it so that you can do high resolution encoding, etc. We're increasing the size of those magnets as much as possible and focusing them on small areas that we care about, like just the head rather than the entire body, in order to go to as high a resolution as we possibly can. And this is just an example image that they picked out from a functional scan. So just looking at checkerboards here, they can actually see different layers of activity. Here you can see kind of like a double hump or a single hump over here, but also how it differentiates from the individual vessels that are running through the cortical areas as well. So that's exciting. I'll also point out that we have a lot of work done on our systems. So this is data that has been recorded on 7TB that uses clever tricks that are kind of learned on systems like these, but applied to more standard 7T systems like ours is currently, in order to, it's not quite the same resolution. You can see here we're below 0.4 millimeters, and here we're below 0.5, but we're getting increasing detail based on how we're sampling, etc. And so these two systems are kind of working together in order to gain as much information from fMRI as we possibly can. And this is my last slide. I wanted to point out a few high-resolution fMRI educational resources. So these are basically places that you can go if you're like, I want to hear more. First of all, ISMRM is a great conference for people who are really interested in how MR works, and specifically for understanding how it can contribute to functional MRI or clinical diagnoses, etc. So the conference itself is great. There are also study groups within ISMRM that I think are really good resources and really good communities if you care about these things. So there are two that I would point out. The brain function study group, which is probably the one that focuses on layer fMRI the most, but I would say it has a whole bunch of different foci. And the high field study group. High field is maybe a little bit more focused on the hardware that gets us there, etc. And how do we create RF pulses, those types of things. In addition, there are some virtual things that are probably also useful. There's a biweekly layer fMRI journal club that focuses almost, I would say, entirely on 7T. Well, almost always. And that is every other Monday. If you are interested in these things, you can either talk to me and I can try to add you to the lists that those go out to, or alternatively, you can go to layerfMRI.com/seminar and you'll learn more there. Lastly, there are also what are called dinners. These come from the idea that at ISMRM one year during COVID, we were going to have dinners where people would give talks. This didn't happen, and therefore they just became virtual, and then they never really stopped. But they are essentially academic talks that tell you more about what's happening in the field. You'll probably also see some familiar faces there, because it's a pretty, I would say, the community that works on 7T and specifically 7T MRI is not super big. So you run into the same people over and over again. And with that, I will ask if there are any questions or anything like that. And we're like exactly on time. That's always good. Yeah.
Yeah, I have one question about acceleration methods with, more parallel receiver coils.
Mhm.
So what is, how is the optimal number of receiver coils determined? Because obviously if you just keep going, and you have so many receiver coils, you're gonna have so many parameters in your linear model that it's gonna be very hard to distinguish where a signal is actually localized.
Yeah.
So how is that sort of determined, and how do we know that that configuration convention is the optimal?
That is a very good question. I would say that what you're talking about in terms of like having too many parameters in a linear system, that can definitely happen. And if we could keep going, we would probably hit that limit. But I would say the more relevant limit, or the one that comes up more, is just that these things are made out of hardware. And that is a hard thing to deal with. So like, in order to have more coils, those coils have to keep getting smaller and smaller and smaller. Their receivers change, etc. Maybe like we can't see as much depth in the cortex because the receivers are so small. These are problems that we run into, but also just the amount of electronics that sit on top of them becomes problematic, particularly if we're talking about also making smaller and smaller systems where less and less can fit in there. And I know that when they were developing this system as well as the 10.5 that's in Minnesota, they actually ran into situations where they overdid the number of receivers that they put into the system, and they end up recalibrating them so that they could take receivers out. And they basically made the decision that like another thing which also affects more and more receivers is that they interact with one another. They're just antennae, so they will have noise correlations between them. And so you don't continue getting more and more gains. So I think that you're right, that there is an optimum. Typically, I would say we are a little bit at the mercy of the vendors because they also give us just an option. So like, if you have a system that can go up to 128, you can optimize up to that point. But oftentimes people just think, I'll just fill up that slot, or the 64 that you're allowed, or the 32 that you're allowed. So we have these little increments, and those are a little bit related to digitization processes that happen in our ADCs, but it's an excellent question. And I think in a perfect world, we would actually optimize that problem.
I have two quick questions. The first is, given the faster T2 star decay, is like multi-echo a challenge?
It is, yeah, for sure. It's a good and a bad thing though. So one of the things that I didn't mention here was anytime you have faster decay, it means your TRs can also get shorter. So yes, you have to have better hardware, and you have to be clever about how you do your imaging in order to image as quickly as possible early in that T2 star decay. But it also means you can restart and do the next TR a little bit faster. So even though you have to image faster, you might get done with the full scan faster as well. And then maybe you can just collect different data or more data, etc. So this is a big advantage of 7T in the clinical realm, is that basically it gives us the opportunity, even if there are engineering challenges associated with it, to make our protocols shorter.
And the second quick question was, are the general denoising procedures similar, or like in terms of just progressing as motionless, or are there like unique considerations for denoising too?
Yeah, so I won't give an absolutely definitive answer because I think you'll hear maybe about this a little bit next week as well. But yes, there are unique contributions. I didn't talk about the balance of the different types of noise that we deal with in fMRI. So there's thermal noise, which I did talk about a little bit. This is just pure electrical or magnetic line noise. And so basically that's random. That is like what we most of the time think of as true noise. Alternatively, and you're pointing out this in saying like, can you regress stuff out? There's also structured noise. So physiological noise is a big thing. breathing and heartbeat contribute a lot to our fMRI signals, and for most studies, we do not consider those of interest to us. There are examples, especially in the clinical realm, where this changes, but blah, blah, blah. Anyway, the point being that the physiological information is probably pretty similar in how we deal with it, because it is just structured. However, if we're pushing to really, really high resolutions, we're actually pushing ourselves into a situation where you start to see grainier and grainier images. And the reason that they are getting grainier is because we're more in the realm of that purely random noise. And there we are able to take advantage of denoising algorithms that are specifically looking at correlations in the images to try to understand which is the random portions of the image and which are the non-random portions of the image. And so there are some examples that we'll hear about next week where those come into play a little bit more. But at 3T, you're not really in this realm so much. Like you're pretty much dominated by physiological noise because your signal is pretty good, because no one pushes 3Ts like so hard that you're in that thermal noise region. That makes sense.
Yeah, thanks.
Anything else? Otherwise, I will let everyone go. Okay, thank you so much.